And as they are running a leaf blower just outside my classroom, I would like to talk about potential energy curves. Potential energy curves is a graphical way to represent conservation of energy. So what we're going to do is we're going to make a graph here, and I'm going to use an example that's pretty famous. It's a graph of potential energy versus position. This could be gravitational or spring or what have you. In this case, I'm going to make a potential energy curve for an atom. And so the potential energy goes up really high at the beginning, then there's a little pit right here, and then it approaches zero and becomes asymptotically close to zero. And if you have an atom that has multiple positions where electrons could be, there'd be another little lump right here. So a couple of things that we need to know about potential energy curves. The first thing is that the force on the electron or whatever is experiencing the force in this picture is going to be equal to negative the slope of the potential energy curve, or minus the change in potential energy divided by distance, or if you're a calculus-enabled person, minus the derivative of the potential energy with respect to the position. All of these things mean slope. So that would mean that for example, right here at that spot where it crosses the axis, the slope is a negative large number, which would mean that the force, so this is force at this point, would be negative of a negative large number, which of course is equal to a positive large number. Okay, so a positive large number. Now, positive means a repulsion. So at this point, the electron will be pushed away from the nucleus, which is at zero on this diagram. What about over here? What about at this spot? Well, here we have a slope that is a positive number, and it's fairly large as well. So the force here is a positive large number, but it's the negative of a positive large number, which means it's a negative large number. Negative forces are attractive forces. So if the electron was here, it would be repelled away. If the electron was here, it would be attracted towards. And that brings us to our first thing, and that is that there are areas of stability. For example, if you got yourself caught between here and here, you would feel a force that would repel you away, and then you'd go over here and you get a force that would attract you back, and you'd bounce back and forth between these two positions right here. You would be bound. So areas that look like they might hold water are areas where an object can be bound. Bound means tied to the system, can't get away. Every time you try to go this way, you get batted back this way. Every time you try to go that way, you get batted back this way. So that's a thing, an object can be bound. So that can happen on this diagram anywhere under the axis, anywhere you're in an area with negative potential energy, you could get an electron that's stuck. If you have an electron that has more energy, and then it would come along here, it would hit this, and it would feel the positive force, and it would be repelled away, and there'd be nothing to stop it, so it would escape. So up here, um, the object would be free. These 2 points where the object would turn around are called, surprisingly enough, turning points. Okay, so when you look at a potential energy graph, you know that you can always get the force back by taking the slope, but it's the negative of the slope, where positive forces are repulsion and negative forces are attraction. Any area on the graph that looks like it might hold water, like if you poured water into it, the water would not run away, is where an object can be bound. Anything that is not holding water is where the object would be free. I mean, it could still interact with the system, but then it would go away. All right, let's. I'm going to clear this up. I'm going to get a new piece of paper and talk about this a little bit. Let's use a different example. This is the potential energy of a spring. And so spring potential energy. And I think I said something that was a little off. The graph is actually energy versus position. But the curve on it is the potential energy. So I think I mislabeled it. This is just an energy axis in joules. Hey, that would be a good idea. Why don't I put the in joules, and this is just a position axis in meters. Now, if we put the potential energy of a spring on this graph, you know that the potential energy of a spring is 1/2 kx squared. So this is a parabola that starts at the origin. So, okay, that's not the best parabola ever drawn in the history of mankind. That's why I'm not a math teacher. You should see my sine and cosine. Okay, so there's our parabola. Now, when you look at this, given what we talked about on the first page, you can see that this entire graph looks like it could hold water. That means that at whatever energy level you have, you can have something that bounces back and forth. And of course, we've seen that with springs. When you have something on a spring and you pull it out to here, it boingy, 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 bounces back and forth. There'll be an entire chapter on that in a month or so. But what I wanted to point out is that this red line is the potential energy. And any energy level that you have with your object that's attached to the spring, so like let's say you pull it to the side here, that means it would go back and forth at this level. This is the total energy, which I call the total energy. I call it the water line, using that analogy. The water line of total energy. And so at any point along this graph, you can find the kinetic energy by looking at the difference between the total energy and the potential energy at that point. The total energy is always a constant. And of course, if you're at either end, it is all potential energy. If you're right here in the middle, it is all kinetic energy. And any place else in the middle, you have a mixture of kinetic and potential. Kinetic here and a little bit of potential underneath, because that's the level of this curve. So in reading potential energy curves, you look at the curve on an energy versus position diagram. You can get your force by taking a derivative or a slope, and it's the negative derivative or slope. You can spot areas where an object might be bound. You can find the turning points by finding areas where it's all potential energy. If somebody asks you how far does this thing move back and forth, all you have to do is take this point and project it down and say it'll go this far back and forth. At what energy does it turn? Well, at this energy right here. So a lot of things you can get off the diagram. And if you can draw your total energy water line, you can always find the kinetic energy at any point. That is the lesson on reading potential energy curves.